Alright, so I'm going to talk to you guys about nuclear chemistry. And I've got some reasons listed why nuclear reactions are different from the chemical reactions that we usually talk about. Alright, so nuclear reactions are inside the nuclei. Instead of whenever you do chemical reactions, you react things with other atoms and other compounds. It's actually inside that one atom that you're talking about. And inside the nuclei, it emits particles and or rays, and it's in just that one atom instead of reacting with other things. Alright, in chemical reactions, normally things don't change from one atom to the other. They just stay the same and react with each other. But in nuclear chemistry, atoms can actually change to others because you are dealing with the number of protons, so whenever you change the number of protons, it changes the atom that you're talking about. And like I just said, it deals with protons, neutrons, and electrons. And in nuclear chemistry, you have large energy changes. And a large energy change is not in chemical reactions whenever you have something explode. It's where something is like an atomic bomb and it destroys a whole city. And that's a large energy change. And in chemical reactions, rate is affected by the concentration, the catalyst. But in nuclear chemistry, it is not affected by any of those. Like if you have a nuclear reaction, the catalyst is not going to speed that up. And over here, I've got an atom drawn, and inside of it, there's the nuclei, and inside of it are all the protons that you've got inside of it. And whenever you think about things, normally protons reacting with protons is going to repel each other, because whenever you have something similar, it repels. But then how are they so closely packed together? And that's where strong nuclear force comes in. It acts on subatomic particles closely packed together, and it neutralizes them so that it makes it so that they can be closely packed together inside the nuclei. And stability in a nuclear reaction means that it's not radioactive. And to figure out if an atom is not radioactive, you do neutrons divided by protons. And if you've got a low atomic number that you're dealing with, it's going to have a 1-to-1 ratio, and that means that it's stable. And if you're dealing with a high atomic number, it's going to have a 1.5-to-1 ratio, which is going to be stable. But anything that's above that, it's not going to be stable, and it's going to be radioactive. Alright, so I've got lead right here. And lead has 82 protons. And to find the number of neutrons, you actually just subtract the two. So you have 124 neutrons. Alright, so to figure out if lead is stable or not, you take the number of neutrons divided by the number of protons, and you're actually going to get 1.51, which is the maximum that it can be, but it is still stable because it is only 1.51.
Erase that. Erase it.
Okay, nuclear notation. It represents decay of one element into another. And this is the basic formula. This is the element and then the mass number and atomic number. An example is uranium with a mass number of 238 and an atomic number of 92. Yields tungsten with a mass number of 234 and atomic number of 90. Plus helium, atomic number 2, and mass number 4. And to get that, you have to add 234 plus 4 to get 238. And 90 plus 2 to get 92. So the top numbers have to be equal to this, and the bottom numbers have to be equal to that.